Wormhole Traveling. Is supersonic travel possible in the future? This question has been haunting many scientists for almost a century. Previously, such high-speed travel was associated only with something paranormal, but now science is not afraid to question the usual way of life and even the laws of physics. So let's get to the bottom of it. Supermassive black holes in the centers of galaxies can be moleholes. Yes, you didn't misunderstand. A molehole, or wormhole, is a specific concept that is explained by an example that you have definitely seen more than once. It has even become a kind of meme that in all feature films where wormholes are mentioned, they are always explained with an example of a piece of paper that is folded in half and pierced with something, showing visually how a wormhole can instantly connect two different points of space. Surely, you have seen such illustrations of moleholes, or as they are also called, wormholes. They are depicted as tunnels that connect two entrances in two different realms of space and time. Wormholes are hypothetical objects, because it is not yet possible to actually implement them. Their existence was predicted by solutions of Einstein's general relativity equations. Black holes and wormholes are special types of solutions to Einstein's equations that arise when the structure of space-time is greatly distorted by gravity. For example, when matter is extremely dense, the fabric of space-time can become so warped that even light cannot escape from it. This phenomenon is called a black hole. Since theory allows the fabric of space-time to stretch and bend, a variety of possible configurations can be imagined. In 1935, Einstein and physicist Nathan Rosen described how two sheets of space-time could be connected together, creating a bridge between two universes. This is one type of wormhole, and many others have since been invented. Some wormholes may be passable, that is, suitable for human travel. However, to do so, they must be large enough to remain open to gravity, which tries to close them. To push space-time outward in this way would require an enormous amount of negative energy. Does that sound like science fiction? We know that negative energy exists. Small amounts of it have already been produced in the laboratory. We also know that negative energy is behind the accelerated expansion of the universe, so nature may have found a way to make wormholes. Since the time of Einstein, scientists have accumulated a considerable body of evidence supported by observations that suggest their existence. Scientific papers have begun to appear that at least suggest a way in which moleholes can be detected under certain assumptions. The authors of the article, which was accepted for publication in the Journal of the Royal Astronomical Society, are astrophysicists from the Pulkovo Observatory. The proposed method is based on the hypothesis that in the center of galaxies with active nuclei may be the inputs of microscopic primary wormholes. Primary moleholes are those that may have formed at the earliest stage of the universe's existence. It is assumed that they must be microscopic, but they are also hypotheses that in an ever-expanding universe, they may have grown to larger sizes. Wormholes can also have powerful gravitational effects on surrounding objects, but the key difference is that an object or radiation trapped in a wormhole can hypothetically leave it. Many assumptions are made here at a minimum that wormholes are considered very unstable. In order for them not to collapse instantly and to exist for a certain period of time, they require extremely unusual mechanisms, like matter with negative energy density and negative pressure, which we have already talked about before. In general, if we assume that moleholes exist at all, and they can remain stable, we can assume the following. Substances that got into one entrance of the molehole can come out from the other side of the tunnel, but at the same time, the same thing can happen from the other side. It turns out that the substance that entered the tunnel from opposite entrances can collide at enormous speeds. The authors of the paper modeled what could happen as a result of such a collision and concluded that this could be how spheres of plasma heated to trillions of degrees could be formed that would emit gamma rays at very high energies. The authors suggest that such gamma rays would have a very charismatic spectrum, which we could try to observe with telescopes. Such specific radiation could serve as evidence in favor of the fact that there are not supermassive black holes, namely moleholes, and in fact speak in favor of their existence. But once again, we emphasize that here all the same a lot of assumptions are made, and so far such a spectrum has not been detected. This radiation may be the key to distinguishing between a molehole and a black hole, which were previously thought to be indistinguishable from the outside. Black holes should produce fewer gamma rays and eject them in the form of a jet, while the radiation produced through a molehole takes the form of a giant sphere. Although the kind of wormhole discussed in this study can be overcome, the journey through it would not be pleasant. It would be so close to the center of an active galaxy that the high temperatures would burn everything to a crisp. but this does not apply to all wormholes, such as those farther from the center of the galaxy. The idea that there may be wormholes in the center of galaxies is not new. Take, for example, the supermassive black hole at the center of the Milky Way. It was discovered by painstakingly tracking the orbits of stars near the black hole, and it was a major achievement for the Nobel Prize in Physics awarded in 2020. But a recent paper suggested that this gravitational pull might be caused by a wormhole. Unlike a black hole, a wormhole can leak some gravity from objects on the other side. This gravitational action would lead to a tiny jolt in the motion of stars near the galactic center. According to this study, the specific effect should be measured in observations in the near future. Unlike a black hole, a wormhole can leak some gravity from objects on the other side. This gravitational action would lead to a tiny jolt in the motion of stars near the galactic center. According to this study, the specific effect should be measured in observations in the near future, when sensitivity of our instruments becomes a little higher. Wormholes strongly capture our collective imagination. In a sense, it is a delightful form of escapism. Unlike black holes, which are a bit frightening because they can trap everything around them, wormholes can allow us to travel to distant places at faster than the speed of light. In fact, they may even be time machines, proving the ability to travel backwards, as the late Stephen Hawking suggested in his last book. Moleholes are recognized in quantum physics, which governs the world of atoms and particles. According to quantum mechanics, particles can fly out of empty spaces and disappear after a moment. This has been seen in countless experiments. Similarly, physicists believe that wormholes may have formed in the universe from the foam of quantum particles appearing and disappearing. Some of these original wormholes may still exist today. Recent experiments on quantum teleportation, the ethereal transfer of quantum information from one place to another, have turned out to be frighteningly similar to two black holes connected through a wormhole. These experiments seem to solve the quantum information paradox, which suggests that physical information can disappear forever in a black hole. But they also reveal a profound connection between the knowingly incompatible theories of quantum physics and gravity. Wormholes are relevant to both, which may play an important role in building a theory of everything. The fact that moleholes play a role in this fascinating research is unlikely to go unnoticed. They may help us understand some of the deepest cosmic mysteries, such as whether our universe is one. Another study by a Harvard physicist also confirmed that wormholes may exist as tunnels in warped space-time, connecting two distant places through which travel is possible. But don't pack your bags and travel to the other side of the galaxy just yet. Although theoretically possible, it is not feasible for people to travel through them, said study author Daniel Jaffers of Harvard University, written in collaboration with Ping Gao of Harvard and Aaron Wall of Stanford University. It takes longer to go through these wormholes than to go through them directly, so they're not very useful for space travel, Jaffers said. He presented his findings at the April 2019 meeting of the American Physical Society in Denver. Despite his pessimism about supersonic interdimensional travel, he said inventing a way to create a wormhole through which light could pass would be a boost to the quest to develop a theory of quantum gravity. The new theory was invented when Jaffers started thinking about two black holes entangled at the quantum level. Although this means that the direct connection between black holes is shorter than the wormhole connection and therefore traveling through wormholes is not an abbreviation, the theory provides new insights into quantum mechanics. From the outside, traveling through a wormhole is equivalent to quantum teleportation using entangled black holes, Jaffers said. Jaffers based his theory on a setup first developed by Einstein and Rosen in 1935, consisting of a connection between two black holes. According to Jaffers, since the wormhole could be passed through, it was a special case where information could be extracted from the black hole. To date, the main stumbling block in creating passable wormholes has also been the need for negative energy, which seemed incompatible with quantum gravity. However, Jaffers overcame this with the tools of quantum field theory, calculating quantum effects similar to the Casimir effect. As for the possibility of human passage through the wormhole, the work of scientists from Princeton University, Alexei Malikin and Juan Maldacen, proved interesting. They used objects orbiting relative to each other as the mouths of the wormhole, which would resemble black holes to an outside observer. To describe the physical properties of the wormhole, important in terms of spatial travel, the authors used the Randall-Sundrum model, which introduces an additional to the known 3 spatial and 1 temporal fifth dimension. Then, using the metric that is the law-defining space-time intervals analogs of distances in ordinary space of this model, physicists obtained estimates of the size of the mouths of the molehole, the length of the tunnel and the travel time through it, which would be measured by the traveler himself and the observer outside the wormhole. Taking advantage of the fact that the tidal acceleration that the traveler will experience through the wormhole is inversely proportional to the square of the size of the mouth, setting the maximum allowable short-term overload at 20 grams. That is 20 times the free fall acceleration at the Earth's surface, and involving experimental estimates of unknown Randall-Sundrum model parameters, the researchers have limited the allowable size of the entrance to the wormhole. As a result, physicists established that a person is able to survive the impact of tidal forces at the size of the mouth of the molehole, not less than 1,500 kilometers. It is comparable to the size of dwarf planets. It would take about 0.15 seconds to overcome such a tunnel on the traveler's watch, and it would take over 9,000 years for an outside observer. At the same time, scientists believe that the distance between the mouths outside the wormhole light can overcome much, up to 1,000 times faster. This allowed to assure the stability of the rotating system and guarantee the passage of the tunnel. The authors note that despite the potential suitability of moleholes for travel, some serious problems remain unsolved. In particular, the mechanisms of wormholes formation remained outside the scope of the study. Another important obstacle is extraneous particles such as photons and relic radiation. First, if they enter the tunnel, their energy will increase many times by orders of magnitude or even tons of orders, making them dangerous for humans. And second, they can dissipate and lose energy inside the tunnel and lead to its collapse, turning the wormhole into a black hole. As you have already realized, humanity is still a long way to travel with the help of moleholes, but who knows? Maybe in a few decades, they will turn from impossible to real, and in hundreds of years, in the usual and everyday.